Hello, Calculus 1 students. This is section 1.3 lecture, and it's all about this concept called continuity. Continuity is it's a way to describe certain functions. Um, yeah, and it's kind of one of those things that you just want to keep in the back of your mind. A lot of the rules that we'll be learning throughout the semester like depend on a function being continuous. So like oftentimes when we look at a theorem, it might say if f of x is continuous and such and such and such and such happens, then such and such is going to happen, stuff like that. So it's not one of those things that you're like constantly like really conscious of, but it is something to like keep in the back of your mind, this idea of continuity. Numbers 1 through 9 are all about continuity. And then intermediate value theorem is actually one of those theorems that requires a function to be continuous in order for the conclusion of the theorem to work. So then we'll look at the intermediate value theorem, which is what numbers 1 through 10 in the homework are about. So I actually wrote the definition for continuity here. But before we look at the definition, I just want to like everybody to kind of have an intuitive idea of what it means to be continuous. So we'll come back to the definition, but just like if you use the word continuous in just like everyday language, for me, when I think of the word continuous, I think of nonstop. Like if I say the I have a really good friend whom I love very dearly. He's actually my ex-husband, and we're really, really good friends. But he is continuously talking, like so much that it really gets on my nerves. So notice how I use the word continuously. He talks nonstop. That's how much he talks. Like it's just nonstop. So anyway, that it kind of means the same thing in mathematics too. Like if you are able to picture like the graph of a function, like here I'm gonna draw some continuous functions. So like the sine curve, like that is considered a continuous function. It just keeps going on and on. Also, like any linear function, that's also continuous. It just keeps going on and on. A quadratic functions also continuous, right? Versus not continuous would be something like a rational function. So, with rational functions, you like have you oftentimes have an asymptote, and maybe something like this will be going on. So, like, where you have a break in the graph, or a function like where you have like, I don't know, maybe it's continuous for a while, but then all of a sudden there's a hole, something like what I just drew. Like if you have a hole like in the graph, that would be considered not continuous where the hole is. Also like piecewise defined functions. So like if I have like a function that maybe is defined like this to the left of a certain number, and then like this to the right of a certain number. This number where there's a jump in the graph, that is where the function would not be continuous. So basically continuous, it means like there are no breaks in the graph. Non-stop, just goes on and on forever. Versus not continuous, you have a break in the graph or breaks in the graph. So that's just intuitively how you want to think of it. And then here is the formal definition of continuity. So we say that a function f of x is continuous at x equals c if all three of these conditions that are listed here, all three of them have to hold for the function to be considered continuous. And by the way, continuous. So oftentimes when we talk about a function being continuous, we talk about it being continuous at a certain point, or sometimes we'll talk about it being continuous at like on an interval. But here and if we say it's continuous on an interval, it just means it's continuous at all points in that interval. So here we're saying f of x is continuous at this number at x equals c if the following three conditions hold. So all three of these conditions have to hold. One, f of c has to be defined. So like if you plug c in for x, you're going to get a real number. Two, the limit of f of x as x approaches c exists. So like the left-sided limit is going to be the same as the right-sided limit, what I talked about in section 1.1. And then last of all, three, the limit of f of x as x approaches c has to actually be equal to f of c. So let's look at some examples where you see like kind of what happens if one of these conditions don't hold. And we'll see in our homework how that happens. So I'm gonna go over to homework and we'll look at there's several examples. I like them a lot because the examples are graphs, so you can really you can look at the graph and just like intuitively what I was saying, if there's a break in the graph, then right away the function's not continuous at that break. And so it's nice to be able to like match the picture with the words in the definition. So that's what these problems do. So here's section 1.3 problem number 1. So it gives us this graph and it says select all the statements below that you agree with. So right away, like just looking at the graph, you can tell that this curve is not continuous at x equals 2, right? You see, notice that there is a break in the graph at x equals 2, like right here. So right away, we can just look at it and tell that this function is not continuous at x equals 2. We know that right away. But let's just look at the three conditions that have to hold. So the three conditions are these right here. So f of 2 is defined. So, and then limit of f of x as x approaches 2 exists, and limit of f of x as x approaches 2 is actually equal to f of 2. So those are the three conditions for continuity, the three conditions that have to hold. And so they want us to check off the boxes that are true. But if all three boxes aren't true, if we don't get to check all three of these, then right away, your function's not continuous, which again, we already know, but let's see which condition doesn't hold. So let's see, going back to our function, to the first condition, f of x is defined, this one, right here. This one actually holds because if you look at the graph, notice that at x equals 2, there is a point on the curve that actually goes with that x value, x equals 2. Like there's an actual point on that curve. It's a closed dot, which means it's an actual point on that curve on this function. And the ordered pair is 2, 1. So yes, f of 2 is defined. We get to check this off. And I can actually say that f of 2 is equal to 1. So 1 is a real number. So we're good for that one. We get to check that one off. The next one, the next condition is saying the limit of f of x as x approaches 2 exist. And so for this one, we want to check the limit on the left and the limit on the right. So if we look for the limit of f of x as x approaches 2 from the left, and then look at the limit of f of x as x approaches 2 from the right, our limit, like the idea is that we want it to, we want to see if they're the same. And if they're the same, then we get to say that the limit exists. So I'm just putting my little x's here with my, so we're going to say x approaches. Let's see if I can write this. Here, I'm going to pause this so I'm not using up time. All right, so I wrote everything that we need to look at. So we're looking for the limit of f of x as x approaches 2 from the left. So notice that I like put a little minus sign to the right of that 2 there. So that means that we're approaching 2 from the left. That's what that means. This means x approaches 2 from the left. That's what that little minus sign means. And then notice for the next one, notice I put a plus sign. So let's see if I can point to the plus sign. See right there? There's a plus sign. And so what that means is x approaches 2 from the right side of 2. And then notice the last limit, it just has x approaches 2, period. Not from the left, not from the right, just period. Oh, well, actually from both the left and the right. So basically, if your limit as x approaches 2 from the left is the same as the limit as x approaches 2 from the right, then the limit as x approaches 2 is equal to that number. If the limit as x approaches 2 from the left is different from the limit as x approaches 2 from the right, then the limit of f of x as x approaches 2 does not exist. So we're going to see left and right. I'll use blue to trace this. So imagine first looking at x approaching 2. So 2 is the number that's circled, right? So imagine going along the graph on the left side of the x value 2. So you have all these ordered pairs and you're letting the x value approach 2. And notice I'm approaching 2 from the left side to see what's going on the left. And it looks like my graph is getting closer and closer to -2. Even though the actual y value is at 1, the graph is actually approaching, it looks like it's going to -2. Like that's where it feels like it's going, although it actually ends up going to 1. We don't know that. And limit is just, I mean, we do know that, but limit is just about what's your graph approaching? What are the y values getting close to as x gets close to this number? And in this case, as x approaches 2, the y values seem to approach -2. So for this one, I would say that my limit as x approaches 2 from the left is actually equal to -2. And then now I'm going to look at my limit as x approaches 2 from the right side. So on the right side of 2, I'm just going along the graph, and look, the y value seems to be approaching the same number as on the left side. It seems to still be approaching this -2 here. And so once again, it looks like the limit on the left, or sorry, on the right, so the limit as x approaches 2 from the right side looks like it's also -2. And because these two numbers are the same, so because this number is the same as this number right here, because they're the same exact number, we get to say that the limit as x approaches 2 of f of x is -2, which means that the limit exists. So I get to check this off and say limit exists. Finally, the third condition is that the limit as x approaches 2 of f of x is actually equal to f of 2. That's our third condition. And this is the one where we have problems. And this is what makes the function not continuous at 2. Because notice earlier, and like while looking at the first condition, I found that f of 2 is equal to 1, right? And then while looking at the second condition, I discovered that the limit of f of x as x approaches -2, as x approaches 2 is equal to -2. And so because those two numbers end up being different, so because f of 2 is actually equal to 1, whereas the limit as x approaches 2 is -2, because they're not the same number, 1 and -2 are different numbers, then we don't get to check off this third box. So so just a little note here. I'm just gonna write a little, what am I gonna do? I'm gonna do this. So just notice that this part, like the limit as x approaches 2, like all of this, that all ended up being -2. That was -2 versus this right here. That was just 1. F of 2 was just 1. And -2 is not equal to 1, right? So these two are not equal to each other. An equal sign with the slash through it. And so put a slash through this to say these are not equal. -2 is not equal to 1. And so that's why I don't get to check off this box right here. And that is actually what makes this function not continuous. So I don't get to check off the function is continuous at x equals 2 because it's not continuous at x equals 2. So I check off the one that says the function is not continuous at x equals 2. In order for the function to be continuous, all three of these have to be true. So notice like that, just like notice that the limit being different from the function's value itself, that's what causes the break in the graph. That's what causes what we call the discontinuity. Let's look at another problem. So problem number 2 says, so it gives us this function. And first of all, I can say right away that f of 2 is defined. Looking at this, I know that I have like a closed point at x equals 2, right? So I can just look at this and say, I know f of 2 is defined. Like this is 2, 0. And so I can actually say f of 2 is equal to 0. That's a closed point. If there were just an open point here, it wouldn't be defined. Like there has to be a closed point somewhere at x equals 2 for it to be defined. And then when I go on to the limit idea, if I take a look at the, I'm not gonna write all this out again, but if I take a look at actually I will, I'll just pause the recording. All right, so we want to think about the limits again. And if I find the limit as x approaches 2 from the left, so that's the first one I wrote down with the little negative sign there, I imagine going on the left side of the graph, like on the left side of 2. And it looks like the graph is approaching 0, right? On the left side of 2. And so it looks like that limit is, I can say that that is equal to 0, the limit on the left, as x approaches 2 from the left. Then if I take a look at what happens, or what my graph is approaching, or y is approaching as x approaches 2 from the right, I'm on the right side right now of 2. It looks like my graph is approaching the y value. It looks like it's approaching -1. So the limit on the right as x approaches 2 from the right is equal to -1. And since the left-handed limit is different from the right-handed limit, since these two are not the same, so this is different from this. So because of that, oops, because they're two different numbers, 0 is different from -1, we would say that the limit as x approaches 2 of f of x does not exist. That's what the DNE stands for, does not exist. And so I don't get to check off the second box. Because the limit doesn't exist. It will only exist if the two sides are the same. And so I don't get to check off the second box, which means I also don't get to check off the third box, because if the limit of f of x as x approaches 2 just doesn't exist, then there's no way for it to be equal to f of 2, which is 0. So I can't check off the third box either. I can only say the function is continuous if I can check off all 3 boxes, which I can't. So the function's not continuous, which you can just tell by looking at the graph, because you see a break in the graph immediately. Just looking at the graph, there's a break at the 2, right? So this time the reason for the discontinuity is that the limit on the left was different from the limit on the right. So let's look at another one, and then actually let's look at number 4, and then we'll look at one of these piecewise defined ones. Wow, these all have twos. Let's look at number 3, because I'm just like, all of them are 2s, but number 3 has a different number. So let's look at this one. So this one says, determine which one of the following rules for continuity is first violated at a equals -1. And so first violated, so it's saying, okay, we know this is not continuous. What rule is violated first? So first of all, I know f of a is defined. F of -1 is defined because I see a closed circle there. So that one is not violated. The second one, the limit of f of x as x approaches a from the left, notice that's 2. But if I take the limit of f of x as x approaches a from the right, I get -1. And since the left-sided limit is different from the right-sided limit, 2 versus, so not sorry, I said -1. The limit as x approaches my a from the right side is equal to +1. And the limit as x approaches a of my function from the, as x approaches a from the left side is equal to +2. And since 2 is not equal to 1, the limit does not exist. So it looks like this is the rule that is first violated. Let's look at one of these piecewise problems. Let's look at number 7. I'm going to write this down on my iPad. So this is number 7, and it's asking, what would the b value have to be equal to in this function in order for f to be continuous everywhere? And with piecewise defined functions, the main thing to keep in mind is like kind of like this picture that I drew right here of a piecewise defined function. The time where you could have a discontinuity or a break in the graph is like wherever there's a change in the function depending on the domain. So if we go to this, oops, sorry, trying to scroll. If we go here to our function, notice where the domain is split. It's right here at this 2. And so we just need to make sure, like in order for there to not be any break in the graph, the left side, the function on the left side of 2 has to be the same as the function on the right side of 2 at x equals 2. Like they have to like meet at that x value at x equals 2. And so I'm going to go ahead and I'm going to plug in 2 for x. So you take whatever number you see here, 2, plug that in for your x, and then set the 2 functions equal to each other. So I have 2 times 2 minus 4 equals -6 times 2 plus b. 2 times 2 minus 4, that's just 0. And -6 times 2 is 12. And so adding 12 to both sides, I end up with b equals 12. And this is my answer, b equals 12. So I'll go ahead and enter that. And that's continuity. That's basically what your continuity homework consists of. Next, let's look at the intermediate value theorem. So in the homework numbers 10, 11, and 12 have to do with the intermediate value theorem. And the intermediate value theorem, it's, so there are like, you know how we have like the quadratic formula to solve quadratic equations, we can use the quadratic formula. We know how to solve rational equations. We know how to solve linear equations. We have processes for solving a whole bunch of equations, but there are some equations that we don't have processes for solving exactly. We can find estimates. The intermediate value theorem is a theorem that, while it doesn't like actually solve an equation for us, it can help us get an estimate for the solution to an equation that we might not have a process for solving. And so basically what it says is this, what's written here. It says that if you have a function that's continuous on the closed interval a, b, so it's continuous between these two numbers, including at those two numbers, and if k is a number between f of a and f of b. So here, I'm just going to draw a picture of what this is saying. I'm going to draw a picture and hopefully kind of make sense of this theorem. Like we'll show why it makes sense. So first of all, it says f of x is continuous on a, b. So I'm just going to put an a here and a b here. And I'm going to draw a continuous graph. You know, here, let me make it a bit less flat there. I want it to be less flat there. So here's my function y equals f of x, right? And so it's continuous because there aren't any holes in the graph, no breaks in the graph, no asymptotes, nothing. It's just going on nonstop, right? And then it says k is a number between f of a and f of b. So here, this right here marks our f of a. And then f of b, I guess, is around here. And it says that k is a number between f of a and f of b. So I'm just going to mark a y value that's between f of a and f of b. So what the intermediate value theorem says is if both of these things are true, then there has to be a number between a and b, or a and b, or A or B themselves, such that f of C is actually equal to K. So this number, we're going to call it C. And basically it's saying if there's a K between f of A and f of B, there has to be some number between A and B, some X value that's going to go with Y value K, right? That's what that's what the intermediate value theorem is saying, that this has to happen, as it must happen. And so the way the intermediate value theorem can be used, by the way, let me just say that this stuff was developed like the 1700s. So like, and the word calculus, think of the word calculate, calculus. So like back in the day when this stuff was developed, like we didn't have like, I mean, I wasn't around then, but people didn't have like calculators, you know? And so it wasn't like as easy to just like estimate the solution to an equation. So like something like this, it feels pretty revolutionary, like pretty exciting. Back in the 1700s, the idea that if you can show that these two things are true, that f of x is continuous and k is a number between f of A and f of B, then you know you will have a solution between A and B. Like and that gives you the ability to start estimating your solution to whatever equation that you can't solve. So I just wanted to point that out, that like, you know, people don't, it's, you might not use it much today because we have Desmos, right? We have all these like wonderful tools, but just imagine how exciting it was back in the 1700s. Let's look at homework. So number 10. Suppose that f of x is a continuous function on the interval -1, 3. So from -1 to 3 with, so by the way, that first condition is holding. Like remember, there were two conditions for this intermediate value theorem's conclusion to work, to be true. One was that your function's continuous, which it is on this closed interval. So from -1 to 3, so yay. So first condition, check. This was the first condition. And then the second condition was that K is a number between f of A and f of B. So like they're basically telling us here that your A is -1, and then the B is 3. Oops, B is 3. So f of A is -9. And then f of B, they're saying, is +9. And then it says f of x, so we just want to see if the statement is true. F of x equals 0 for some x in the interval -1 to 3. So we think of like whatever f of x equals, think of that as your k. So in this case, it says f of x equals 0. So that means my k is 0. And then the question is 0. So the first condition for intermediate value theorem is that your function's continuous on A, B. That holds, that's check. Second condition is that K is a number between f of A and f of B. And so if my K equals 0, I just want to ask myself if this is between my f of A, which is the -9, and my f of B, which is +9. And yeah, that's true. K is between 0 is between -9 and +9. So I get to say that this is true because both of those conditions hold. Let's look at another one, then we'll end the recording. So let's see, let's look at number 11. So this one, notice something. It starts off with, suppose f of x is a function with f of -1 equals -7 and f of 3 equals 7. So like right away, it's not saying that the function's continuous. So, and then it says, for the statement, it gives us f of x equals 0 for some x in this interval, -1 to 3. So, I mean, first of all, like, again, if you think of your k as 0, we can actually say that k equals 0 is between f of a, which would be the -7, and f of b, which is the +7. So 0 is between -7 and +7. So that holds. The thing is, we don't know if f is continuous on the interval that we're given, which is basically -1 to 3. So that's the thing, is we just don't know if the function's continuous. So because we don't know if the function's continuous, like here is what the graph could look like. The graph could look like this. Okay, so I'm just making something up so we can kind of picture. Let's say here's -1, and let's say here's 3, right? So -1 here, and then 3 here. And again, I don't know if this graph is continuous. So and then we have 0 here, we should say. So I'm going to go ahead and just kind of sketch something. I don't know, I'm just going to make something up. So let's say we have something like this, and then it hits at the x-axis. Let's say that there's a hole there, because we don't know if it's continuous. So let's just say that there's a hole there. I'm just making it up. And then we have something, I don't know, something like that, whatever, right? If there is a hole and that hole happens to be at 0, then there is not going to be some x between -1 and 3 such that f of x equals 0. So it won't be true if it's not continuous. If it is continuous, that means that this part would be filled in and there would no longer be a hole there. But the thing is, we just don't know. So, but if it is continuous, then it would look like that. And then it would be true that there is an x between -1 and 3 such that f of x equals 0. So for this one, I get to mark sometimes true, sometimes false. So try the rest. We'll try these and enjoy the rest of your day. Bye.